Our first talker for this session is Ruben Mak, who's a co-founder of PyData in Eindhoven. He'll probably correct their pronunciation, and presented a couple times at PyData Amsterdam. Founded Bayesian statistic, causal inference, and differential privacy, working with his amazing colleagues on cutting-edge technologies defining the future of the advertising ecosystem. And since this is his time, I'll let him take over. You have it.
Well, welcome everybody, and thanks for choosing my talk. And I honestly hope to raise some awareness for attenuation bias during my talk, because I think it's a common problem and is largely overlooked at the moment. Also, I'll explain to you a powerful but simple trick that we use at Greenhouse to account for attenuation bias in geo experiments. So before we kick off, very brief introduction about my company. I joined Greenhouse 10 years ago, and we're a digital marketing agency inside the Netherlands. A couple of years ago, we were acquired by WPP, and WPP is globally one of the largest media communication company holdings. So we've always had quite a substantial data and technology department within Greenhouse. And currently, some of our technologies are being used across the world within the WPP network. So let's dive into our topic. Before I explain attenuation bias, I would like to talk about the terminology of bias itself, because I think it's used for many things, also inside our field of expertise. So you might be thinking about something like gender bias, a model treating male and female in a different way. Well, this definition is quite close to the general definition, and it has something about ethics to it. But there are many other things which we call bias, which is a little bit less obvious. So maybe in statistics, we're discussing a biased estimator, which means that the expectation of our estimator is something different than what we try to estimate. So of course, this is a very different meaning. It's maybe something you do not like, but there's not really an ethics part to it. And then, for example, in causal inference, confounding bias is you're measuring or you're calculating a correlation rather than a causal effect. And there are quite a few of these kind of biases, like selectivity bias and adaptivity bias. And then in the top right corner, there's a machine learning engineer, and he's thinking, what's all the fuss about bias? I'm just talking about some parameter in my weights and biases in my model. Well, obviously, I'm not talking about this last one definition of bias, because I truly think it's an odd one out. So please allow me to give my perspective on bias for this talk, which I will use to explain attenuation bias. So the perspective I'll use for the talk is bias as being computing something different than you intend to do. And I'll use this to explain what attenuation bias is. So let's take the very simple example of a linear regression. So what you aim to do is to have an estimate for your beta, which is the effect or coefficient of the true x. However, what might be happening in reality is that you're not observing your true x, but a noisy x instead. So if you, for example, apply OLS, you're not computing beta hat as a coefficient of your true x, but of the noisy x instead. And I'll show you now how this creates bias in your results. But first, be aware, attenuation bias goes by many names, including measurement, error bias, and regression dilution. So here's a simple example of a linear regression, with the only difference having a sigma x is 1 here, which is the same as sigma y, which we will be using. So if a true x, which is used in the calculation of y, however, we also have our observed and noisy x with added noise of scale sigma x here, and that's the only one we can use in our regression. So let's see what the results look like. So here's the full results, but what we really only want to look at is our confidence interval for our estimate beta hat. And as you can see, the true beta 2.5 is well outside of the confidence interval. And this is not something that we want, right? So this is us observing the attenuation bias. So when should you be aware of potential attenuation bias? First of all, there might be noise in your observed X. But you care about what happens to Y when the true X changes. And what this says is that you're actually doing inference, not just plain prediction or classification. If you're doing plain prediction or classification, then you do not need to worry about potential attenuation bias. However, in my experience, many projects that start off as a plain pure prediction or classification project turn out to be inference projects when they are applied in business. And to explain why, I conducted a very short story for you, and I hope you can recognize it from practice. So in the story, there's a manager and a data scientist. And the manager is asking the data scientist to build a model to predict sales. He's very confident this will be super useful. But the data scientist is asking how exactly does this generate business value? At which the manager replies that he doesn't know exactly, but is really confident that it will be valuable. So the data scientist goes to work. And 2 months later, she has finished her model. She has this amazing model that's predicting sales with a super small prediction error. At which the manager replies, awesome. Now let's predict what happens when we change the price to decide whether to give a discount. And now suddenly, because of how the model is being applied, the problem completely changed from a prediction problem to an inference problem. And I think this happens quite often. And it's really important as a data scientist or working in the field of expertise that we do know whether we're doing prediction or we're doing inference, because it really matters on how we approach the problem. Attenuation bias is one of the reasons why it is important to know upfront what you'll be doing. So, of course, it doesn't only apply to the linear model. In general, if you care about what happens to Y when a true X changes, you need to think about potential attenuation bias. And of course, there's a very strong connection to causal inference. Because in causal inference, we do not care about what happens to Y when the observed X changes, but what happens when we influence the X, which can be something completely different. So from that perspective, we need to think about, okay, maybe the observed X is noisy, but what we're influencing is not the noisy observed X, but is the true underlying X. So why do I think attenuation bias is overlooked? Firstly, because of all the great breakthroughs in recent years in machine learning, a lot of focus has gone to the prediction part of it. So I'm very happy to see that in the more recent years that the causal inference got a lot of more attention, which is a good thing if you ask me. And second, academia are conservative in rejecting the null hypothesis. And this one I should explain a little bit more carefully. So there's something special about attenuation bias because we do know the direction of the bias. It's always towards zero. So whether you have a negative or a positive effect, the effect is always less strong if attenuation bias occurs. So the result is that in academia, if there is a significant effect found without accounting for attenuation bias, there will be a significant effect for sure. However, if we incorrectly account for attenuation bias, we might be falsely rejecting the null hypothesis and coming to a wrong conclusion. So, while this might make sense from an academic perspective, in practice, underestimation can be just as costly as overestimation. And I'll show you with the example of geo-experiments later on in this talk. So, how can we account for attenuation bias? There's a family of traditional solutions, including the Ming regression, orthogonal distance regression, and total least squares. And I'll be showing you orthogonal distance regression later on. And then there's a new family called error in variable models, which includes flexible Bayesian methods, and they normally use latent variables. And there's some very recent work in how you can apply these models in deep learning in this paper from May 2021. So this is great, but in my experience, these error in variables models can be quite sensitive to model specification. So what this means is that you might still get biased results. If you're interested, I have a repo here where I show some examples that illustrate how sensitive these models are, and you might still be getting biased results. And then there's the proposed solution of this talk. So it only works for binary treatment, but it is a very powerful and simple trick. And I'm quite surprised that we have been using it for quite some years, and I've never heard about anybody else using this trick. So I hope it will be helpful to you. So let's first give an example on how we can solve the attenuation bias using orthogonal distance regression. So there's no package to solve attenuation bias in stats models, which indicates it's overlooked if you ask me. But SciPy has the ODR package. So again, we see that sigma x is equal to sigma y here, which equals 1. And then we simply execute the regression. So as you can see here, now we get unbiased results. This is what we want. But be aware, because we're making an assumption here, we assume that sigma x is the same as sigma y. And this is important when you work with attenuation bias. You need to know at least something about sigma x, sigma y, or the ratio between the two of them. And I can show you in this example. In this example, sigma y is 0.1 and sigma x is equal to 1. And you can see below that we get biased results again. So how can you account for this in the ODR package? You can see here that you can simply pass sigma x and sigma y into the model, or into your real data actually, before you estimate the model. And then we get unbiased results again. So keep in mind, you need to know something about sigma x or sigma y. So onto our topic, geo-experiments. Geo-experiments are done by doing an assignment of treatments to different geographical regions. As an alternative to A/B testing. While A/B testing is maybe more powerful and more common to do, in some cases, we simply cannot conduct an A/B test to test some things. So one of the reasons is that sometimes the outcome cannot be measured in treated and non-treated groups. For example, two of my colleagues contributed to a paper which studies the effectiveness of mobile ads on store sales. Of course, you cannot measure whether somebody was in a treated or non-treated group when somebody's buying something inside a store. The second reason is that in many cases, it's impossible to measure the non-treated outcome, for example, in Google search ads. So we are allowed to do some measurements if we're showing an ad to a user, but we want to test against not showing this ad. And if we're not showing an ad, we are not allowed to make these kind of measurements. So let's go a bit deeper in why exactly do we want to experiment in Google search ads. So in Google search, on behalf of our advertisers, we are placing bids to become have our ad or the company's ad in the top position of the search engine. So if people click on this ad, the advertiser pays for the ad and the user might go to the website and maybe do a purchase. However, not all of these purchases might be truly causal. The reason for this is that if we would not have been showing the ad here on top, the user might still be able to go to and navigate to your website. So one thing could be that they use the organic search results to navigate to your website and do the purchase. The other one could be that they use to go directly to your website or maybe through a bookmark. So not all of these sales coming out of the clicks coming from these paid ads might be causal, but if we do an experiment, we do want to make sure that we do not underestimate the effect. If we underestimate the effect, our bids might become too little and we might not be shown on top and users might not be able to find a website or go to a competitor. So this is why underestimation is just as bad as overestimation. So geo-experiments, what do they look like? There's a great paper by Google explaining how they can be done. In the United States, there's something called designated marketing areas, and those are often used to do these kind of experiments. In the Netherlands, we normally use the provinces to do this kind of experiments. Then there's also a paper by Google in 2017, which discusses a slightly different method. It's also discussing orthogonal regression, but it's not really strongly advising to do this kind of attenuation correction because they found the variance is really high. So I don't completely agree with what Google is saying here, because I think you should always account for attenuation bias in geo experiments, or you'll be underestimating your effectiveness. And with the solution that I'll be showing you in this talk, it doesn't have to be hard to do so. So a very simple example of what the data looks like. So in this example, we only have 2 time periods and 2 geographical regions. So this is in practice much too little data to actually have an estimate, but for clarity, I'll show you what it looks like. So we have 2 time zones and 2 geolocations, geographical areas here. And then in the first time period, none of them are being treated. And in the second period, only part of them are being treated. And this you can use to do a calculation of the causal effect of noise. But why exactly do we need to account for attenuation bias in geo experiments? So of course we have a noisy X, but why is this X exactly noisy? So what we want to know is the effect of the treatment, which is showing X or not showing X. However, what we observe is geo, which is a noisy X, for 2 reasons. One, different technologies are used for estimating location, and some of them are noisy. For example, in Google search, your phone might be using GPS to do a location estimate, which is not always super accurate. However, if you go onto a website, IP address is used to give an approximate geolocation, which is much more noisy than that one. And of course, if you buy something in a store, you maybe have the most accurate estimate. The second reason is inside the experimental period, people move between treated and non-treated regions. So as a result, those people are not completely treated or non-treated, but something in between, making a noisy X. However, there's a good news also. Under some assumptions, we have data to estimate sigma X, so we can account for this attenuation bias. So our proposed solution, it's a simple but powerful trick, and it only works for binary X. So if you think about a binary X being noisy, you know this is a Bernoulli distribution. So the Bernoulli distribution has this property that the variance is a function of P, of this parameter of your Bernoulli distribution, P. So this also implies that if we know sigma X, we can compute Px for sure. And the solution is very simple. Just use Px instead of the binary X to run your analysis. So what does this look like in the data as an example? So instead of having a 0 and a 1 for treatment, we get a 0.15 and a 0.85 inside here. So 0.5 is the Px for the non-treated while you're doing the experiment, and 0.85 is the Px for the treated during the experiment. So what's the intuition? It's very easy. Geos aren't fully treated non-treated, but partly treated non-treated. And the same thing can apply at the user level. So let's take our generic example, and I can show you how it works. So now, instead of having a sigma X, we have a Px of 0.85. So what we do here is that we apply noise according to Px. It's done here. And we again make X noisy, and the noisy X is what we can use in our regression, but the true X is what's actually being used to construct our Y. And you can see, yes, we have biased results again. So same thing when we have a binary X. And solving this problem is really easy and straightforward. We can just call the function apply P, which is simply saying if it's treated, then we use Px, and otherwise 1 minus Px. And then we use P to do a regression. It's a simple and powerful trick because now we get unbiased results again. In fact, this solution is much better than applying ODR in this case, as we can see here. So we can compute sigma x with the formula shown before out of our px here. And then again, we pass sigma x and sigma y to ODR. But what happens is we get an overestimation of a parameter. The reason this is the case is because in ordinary linear regression, it doesn't matter when you have a binary variable in your x. However, in this orthogonal distance regression, we assume that the noise inside of x is normally distributed. And you can easily see if you look at sigma x, this is a standard deviation. So if you apply this to 1 and 0 values, then you'll go well beyond and below 0 and above 1. So that's why we have an overestimate. So in case of binary x, just use this trick, don't use ODR. So what are the applications? So for us, we apply this trick for analysis of our geo experiments. In fact, we don't do simple linear regression, but some more advanced Bayesian analysis. Second, this can easily be applied to double machine learning and other methods for causal inference. Also, when you're imputing missing data, you should also be aware of attenuation bias. And Ruben suggests adding noise to make imputed data more realistic. However, if the imputed variable is used for inference, if you ask me, we'll be introducing double attenuation bias, which leads to underestimates of your effects. So for binary variables, you can just impute px instead. And last, there's some recent work about the use of machine learning classification inside research, which these results are being used in regression analysis. Of course, this leads to attenuation bias. In this working paper, there are several solutions being mentioned, but not the simple trick that I'm showing you in this presentation. So I hope this trick can be useful to researchers also. So thanks a lot for your attention. So let's really recap the main takeaway of this talk. When should you be aware of potential attenuation bias? So there might be noise in your observed x. You care about what happens to y when the true x changes. And you're doing inference, not playing prediction or classification. And as I shared with you before, in my experience, many projects start off as a prediction problem, but when you apply them to business, they often become an inference problem. In that case, you should be aware of potential attenuation bias. So there's some thanks I want to give. Tobias Klein, professor who supervised my thesis, and we have jointly supervised many thesis students afterwards. Koen was one of them, and he wrote his thesis about attenuation bias in geo experiments. So a lot of thanks to him. Also, my two colleagues Menno Zevenbergen and Mark van Zuilen, who together with Professor Ernst Ozinga published a paper about the geo experiment studying the effect of mobile ads on offline sales. And then, of course, Google for publishing the white papers on geo experiments. So thanks a lot for your attention. Are there any questions?
All right, come in. How do you what do you think about estimating P of X for ODR?
I'm not 100% sure whether I understand the question correctly, but the main thing is if you know your PX, then you don't need to do ODR, right? It's really an alternative to doing ODR.
All right, another one. If there is time, if you could elaborate again how attenuation bias and causality are related. I did not fully understand that part.
Yeah. So here's the intuition, at least, if you are thinking about causal inference. So you're thinking about, okay, you can think about the do operator. So what exactly will I be changing, or what will I be influencing inside my X? And that's your causal effect, right? Your causal effect is, okay, what happens to Y if I change my X, which can be different from the observed changes in X. So the relationship is that I think it's a very good framework, this causal inference framework, to also think about attenuation bias. So it might be the case that you're observing a noisy X, but you're influencing the true x that's underlying. So let's a little bit of an abstract example, but let's say you have a noisy x and you know for sure that you can do +5 on this noisy x, and the difference will always be +5. Then in fact, you're influencing the noisy x and not the underlying true x. But I think in many cases, it won't be like that. So if you do treatment or interception, you'll be influencing the true x, and you only can measure the noisy version of x. Another thing that might happen is that you might have a noisy x, but once you start influencing the noisy x, you will be able to actually measure the true x instead of the noisy x. And this is a slightly different topic because, well, then you need to think about it in a different way. It might actually be the case that if you only use the data after doing the intervention, you don't have a noisy x anymore. In general, you also need to account for it if the amount of noise in x changes, but that's a little bit of a different topic. I hope that answered the question, or at least a little bit the intuition behind it.
Oh, yeah. Thank you very much. Those are very interesting, sort of like getting into different world. Because you generally these days you hear about like, you know, like bias. It's sort of these like grand ones, like and like social aspects, and then we get and drill down deeper into different aspects of that. Anyways, thank you very much. I was definitely very glad to be able to moderate for you.
Yes.
I hope you enjoy the rest of the conference and, you know, the week in general. All right.
Thank you. All right. Thanks for hosting.
Yeah. Have a wonderful day.
You too.